Yes, good morning, everyone. I'd like to give you some overview of the things we have been doing based on gradient flow. And mainly I will be talking about renormalization group beta functions, and at the end I'll touch on further applications we are working on right now. So on the top here you have the QCD gradient flow equation, and thought I turned it off, not successfully. So here's the QCD gradient flow equation. It's an ordinary differential equation. And basically what we need to do is we need to define with this the float field B, and therefore we can use basically any Young-Mills action. And in the original formulation from Lüscher, he introduced the gradient flow equation on the lattice and used for the Young-Mills action just the simple Wilson action. And so we talked mostly about Wilson flow. The second popular choice I will be using is a semantic action, so semantic flow. And if you work on the semantic improvement program, you can study the discretization effects of the gradient flow and remove order A square discretization artifacts. And you do that by having two additional terms. I refrain from writing them down. It gets a little bit ugly. But that version of the gradient flow is then referred to as the Zeuthen flow. And in the following, I will use these three versions of the gradient flow. Now, everyone these days is using the gradient flow for scale setting. And this also goes back to Lüscher's work. So you basically start by defining a gradient flow renormalized coupling, where this coefficient n here is normalized to match the convention in the tree-level MS bar scheme. And what we have to do is we then have to estimate the energy density given by this operator as operator E as a function of the flow time. Typical choices for the energy density are either the plaquette or the Clover operator, but you could also use the semantic operator, so plaquette plus rectangle term with the appropriate weights. And you can, of course, construct whatever other operator you feel like doing. And the gradient flow T naught was then defined by Lüscher for the quantity T square E to hit the value of 0.3. And at that flow time, you read off the scale T naught. The Wuppertal group then introduced a variant called W naught, where you basically look at the derivative and ask that the derivative takes the value of 0.3, and that is then called the W naught scale. Now you can go further, and in particular if you're looking at calculating renormalization group beta functions where we are exploiting the finite volume and we work in small lattices, you need to be aware that there are certain corrections. So the first and most important one is the so-called zero-mode correction. The gradient flow was previously shown to be defined in infinite volume. But of course, if we want to use the finite volume to define, for example, later on the step scaling function, we are working in finite volume, and the non-Gaussian zero modes are present, and you have to treat them exactly. And you can do so by integrating them out in perturbation theory. And this was shown by Daniel Nogradi as part of the collaboration with Wuppertal. That is the first correction we are using. Further, you can study the discretization effects and calculate what we refer to as the tree-level normalizations. So at tree level, you don't worry about fermion effects because obviously fermions are only part of the loops. And then you can calculate the corresponding coefficients to further reduce discretization effects. And you need to calculate these coefficients here using lattice perturbation theory. And you need to say which gauge action, which gradient flow, and which operator you use to determine then the energy density. Now, this is one of the standard plots where you see on the left the T square E as a function of the flow time. And in this case, you see that we use the Zeuthen flow for the three different operator choices, C for Clover, W for the Wilson plaquette, and S for the semantic operator. And what you are after are these linear ranges where you then find somewhere in the range of 0.3 the value of T naught. And you see there are discretization effects depending on which operator you use to define T square E. And you can likewise also use other scales. And in particular, what we did in this work with my master student, Christian Schneider, is to look at discretization effects. So we defined a second scale, T2, and we're looking at ratios. Now, the important thing about these gradient flow scales is that they have a continuum limit, and that if you use some global fit, you can define the values of square root T naught or W naught in the continuum limit. And that has been done by several collaborations, and there exist corresponding flag averages. So with these values, you can essentially turn any determination of square root T naught into a physical lattice scale in Fermi. So this is a shortcut to the scale setting. And what I'm showing on these plots here are the set of RBC UK QCD's 2+1 flavor Shamir domain wall fermion and Iwasaki gauge fields ensembles. And we basically repeated this set for the coarse lattices, the medium, the fine, and the very extra fine, which has some other properties. And what you then find is kind of that the linear scaling behavior in A square is not really met by the coarsest lattices. But on the other hand, you observe that the approach to the continuum is flattest with the smallest amount of discretization errors for the Zeuthen flow with semantic operator. This is kind of incidental. This was not the predicted or expected outcome. And it's kind of an interesting observation at this point. Now let me move on to the renormalization group beta function. As you all know, the beta function encodes the depending of the coupling on the energy scale mu. So there is no explicit dependence on the energy scale mu. It's only implicit through the coupling. And in some sense, this is the holy grail for gauge fermion systems. If we know what the beta function is doing, we can predict whether we have a chirally broken system, whether we have a conformal system, whether there is an infrared fixed point, or whether we have something very interesting like an asymptotic safe system with an ultraviolet fixed point. And so people have been calculating this quantity, and in the MS bar scheme, even up to 5 loop orders are known. So I should say that 1 and 2 loop are universal, and then you are scheme dependent in how you calculate the beta function. And we are working in the gradient flow scheme, and Robert Harlander and Tobias Neumann on the perturbative side calculated the RG beta function at 3 loop in the gradient flow scheme, and I will show some interesting comparisons later on. So in general, we have the situation that perturbative predictions are, of course, reliable or usable at weak coupling. And as soon as you move on to stronger coupling, at some point you will need non-perturbative methods. And that is the motivation for our work. So originally we were interested in trying to identify which SU3 gauge system or how many flavors you need for SU3 to find a conformal system. So the onset of the conformal window. And for that we started out using the gradient flow version of the step scaling beta function, which goes back to the original work from Lüschers in the early 90s. And the idea is that you use the volume of the lattice as the only scale in the system. So you generate symmetric L to the 4 volumes. And then you can determine the beta function by calculating this, the scale change. So you have a volume L and you do a scale change S. So the next volume you would need would be S times L. So again, the input is the gradient flow renormalized coupling. And I now put in here the correction factor, which either takes the zero mode correction or our tree level improvement coefficients. And then we determine this coupling here. I introduced a scheme parameter C. And with this relation here, square root AT related to C times the size of the volume L, You then have a way to define a renormalized coupling at a certain scheme. And from that, we can then calculate the scale difference between the coupling on the scaled volume S times L and the volume L, normalized by the log of the scale change. And this is then a discrete step scaling function. It still depends on the scale size L, and we have to send L to infinity to remove discretization effects and take the continuum limit. Now, a plot says usually more than many words. So this is an example for our work with SU3 and 6 fundamental flavors. So you generate first an 8 to the 4 volume, for example, and then a 16 to the 4 volume. You calculate the difference. These are the red triangles down here. And then you repeat the same exercise for 10 to the 4 and 20 to the 4. The orange data points, 12 to the 4, 24 to the 4 in green, 16 to the 4, 32 to the 4 in magenta, and in purple, 20 to the 4 and 40 to the 4. The next step in our analysis is that we perform a polynomial interpolation. So we have values at each value for the renormalized coupling, and then we basically do a vertical slice and take the infinite volume continuum limit, which is shown on the right for selected values of G square. And either we perform a quadratic extrapolation in A square using all volumes, or a linear using only the 3 largest volume pairs. And we get very consistent results at the continuum, which is on the left axis. The corresponding p-values are shown in the plot in the bottom. And the final result is then the black line with the gray arrow band for the linear fit, and the dashed dotted line with the dotted arrow band for the quadratic extrapolation. Now, in this case, I show the data with Zeuthenflow and semantic operator. On the plot on the right, you already saw that these were the red data points with the red and orange lines. The blue data here with the green and blue bands correspond to the same analysis using the tree-level improved Zeuthenflow semantic operator. And what you see here, it's much flatter for most of the area. So we see that the data points in the plot on the left move more on top of each other. But as you can read off here, the extrapolations are very consistent. In the end, you see that up to a certain coupling, this tree-level improvement is really working. But then you get more curvature here. So at some point at strong coupling, the tree-level improvement stops working. So we are away from where perturbation theory is fully working, at least. Now, I could walk you to the same analysis for 4, 8, 10, and 12 flavors, but the plots are in the back. Let me instead show you the final results as an overview. So in red, we have NF equal 4. The bands are our non-perturbative result. The dashed lines are the universal 2-loop result, and the crosses are the 3-loop gradient flow result from Harlander and Neumann. In orange, NF equals 6. NF equal 8, this greenish color. The darker green is then NF10, and NF12 is on the bottom in blue. And what is noticeable is that we assume that NF equal 12 and NF equal 10 will have a fixed point, although we cannot resolve it yet, whereas 4 and 6 flavors are clearly chiral broken, and we have no indications of any turnaround. What NF equal 8 is doing, we can't say. The other peculiarity is that the gradient flow, 3-loop gradient flow result is always seeing some inflection point and would always predict an infrared fixed point. That is very puzzling and disturbing, and no one has a good answer to that. On the other hand, if you pay close attention, for example, for NF equals 6, you do see that the crosses sit much longer on our non-perturbative result than, for example, the 2-loop result. So in the range where perturbation theory works, the gradient flow 3-loop result is giving us the better prediction. And of course, for the much more perturbative system with a weaker infrared fixed points like 12 flavor, it's almost perfect, and the range here is very, very hard to resolve because the beta function is very tiny. The gradient flow result, yes. If I would continue, you see here the universal does not have a fixed point, except for 12 flavors. If you go to 3 and 4 loop, MS bar scheme, there would be a fixed point for NF8, 10, and 12. 6 flavors, you would not see a fixed point, but it would be even faster running, so they move further away from the non-perturbative results. And the 5 loop is doing very crazy things. It basically goes straight and then suddenly shoots up for 10 and 12 flavors. So for 5 loop, you would not expect any fixed point for NF up to 12. And no one knows what's really happening there. It's clearly, if you go to strong coupling, things are not converging. Now, if you want to move beyond step scaling, there is basically the idea that the gradient flow can mimic a renormalization group, real space renormalization group transformation. So the idea is that we have different Bayer actions, and as we run and flow the gradient flow, we are approaching the continuum physics on the renormalized trajectory, which originates from the Gaussian fixed point. And so Anna and Ethan, together with the Andrea Caruso, pointed out that you can essentially turn the gradient flow into an RG flow by adding some coarse graining. And what you then do is you relate the gradient flow time to the RG scale change B, and that you can basically then allow you to directly use the gradient flow time to calculate the derivative and obtain that way a continuous version of the beta function. And since I'm running out of time, this is the result for NF equal 2. So it's SU3, 2 light, or I should say massless flavors. We see the fast running coupling. And what is very barely visible, our continuum limit is the little gray line showing up behind the data points. The data points are the different simulations at the Bayer couplings as before. And what you now see is that we are able to follow the renormalized trajectory a little bit at weak coupling, and as we approach stronger coupling, we are following for a longer time. And in fact, there are always 2 symbols on top of each other, showing the 24 cubed and the 32 cubed symbols at the same beta, and they are just sitting on top of each other. So there's very little discretization effect. And you observe that the non-perturbative result sits between the 1 loop and the 2 loop result, whereas the 3 loop gradient flow is again showing some funky behavior. And come to the almost last slide. So what we are currently doing is we are pushing these simulations to stronger coupling, and you are now going out to G square 11, 12, and we want to get out to G square 16 essentially. And that way we would then be able to define a gradient flow lambda parameter, where we then just have to integrate the RG beta function from the confining regime all the way to the weak coupling regime. And you see here some preliminary result, which is close to an determination by the alpha collaboration. But we are struggling here because these simulations get really hard. And of course, in the confining regime, we cannot do zero mass simulations. So we are doing finite mass simulations and then having chiral extrapolation on top. Now, let me quickly summarize, or better just mention the future applications. So I mentioned the lambda parameter. The next big thing we are trying to get finalized is looking at anomalous dimensions. So there we are using then the fermion flow and study how different 2-point functions evolve to extract the anomalous dimensions. And that scheme is very close to what, for example, Suzuki et al. Have been doing to use the gradient flow as a renormalization scheme. And that is typically related to the short flow time expansion. And there we are talking to Robert Harlander and others. And since there's so much happening, I should use the last seconds to make a little bit of advertisement. In March, we are having a workshop on gradient flow at the ECT Star in Trento. And before I end, I should acknowledge the resources. Of course, Peter Boyle for GRID, which has been essential to generate all the gauge field configurations, and thank my collaborators. Thank you.